Hello, everyone. Today, I'll be introducing our recent research work, FADATest, Fast and Adaptive Performance Regression Testing of Dynamic Binary Translation Systems. I'm Jin Wu. My collaborators include Jian Dong, Rui Lifeng, Wen Zhang, Wenwen Wang, and Decheng Zuo. This is a joint research work by Harbin Institute of Technology and the University of Georgia. Let's first take a look at what dynamic binary translation is. In general, dynamic binary translation, or DBT for short, translates the guest binary code to the host binary code. Here, the guest and the host can be different architectures. Therefore, this allows executing guest instruction set on a host machine. After translation, the generated host binary code is executed to emulate the guest functionality on the host hardware. For example, with DBT, we can execute native ARM applications on an x86 machine. With this capability, DBT can enable many important applications. For example, major computer companies have used DBT to support product transition, especially when the product is upgraded or extended to use a different computer architecture. A recent example is Apple PC, which switched from x86 to ARM. It provides a software layer to run unmodified x86 software on ARM devices. Other applications of DBT also include consolidating multiple heterogeneous servers into a single server, offloading computation-intensive tasks from mobile devices to remote powerful servers, developing and testing mobile apps on desktops, and playing mobile games on desktops. Although DBT is the key enabling technology of these applications, it is not easy to develop and maintain an efficient DBT system. First of all, DBT needs to translate the guest code to the host code in order to emulate the computation of the guest code. Due to the semantic gaps between the guest and the host instruction sets, the generated host code usually includes much more instructions. This brings very high performance overhead to DBT systems. Besides, a DBT system usually has a large code base. This is because it needs to support multiple host and guest architectures. So it is quite challenging to maintain the performance of a DBT system. Even worse, to support more hardware features, the source code of a DBT system is updated very frequently. As a result, any code change may potentially cause performance issue. If there exists too many commits between two versions with a performance issue, it is very hard to figure out the root cause of the issue. To understand this problem, let's see a real example, QEMU, which is a popular DBT system. Its code base has more than 2.8 million lines of code. Every day, on average, QEMU developers submit 10 commits to the code base, and each commit includes 25 lines of code. To maintain the performance of this system, any potential degradation needs to be discovered as early as possible. If a performance issue is found after a certain amount of commits, it is hard to debug and locate the problem. So to monitor and maintain the performance of a DBT system, it is necessary to compare the performance before and after each commit, which is known as performance regression testing. Let's see what is performance regression testing. In general, performance regression testing is a technique to expose performance issues by comparing two versions of a software system. The testing results can tell the developers whether the new version has a performance issue. With the testing result, developers can fix the performance issue if it exists. By applying performance regression testing for every code commit, a performance issue can be discovered at a very early stage. This can mitigate the engineering effort for maintaining the performance of a software system. Unfortunately, for a DBT system, it is hard to take performance regression testing for every commit. To understand why, let's see how the performance of a DBT system is tested. A widely applied approach is using standard test suites, such as spec CPU or parsec. These test benchmarks are well designed, and the testing results are accepted by the state of the art. However, simply applying these test suites for performance regression testing of a DBT system does not work. The reason is that DBT system introduces significant performance overhead, which can be as high as 10 to 100 times compared to the original execution. For example, our experience shows it takes over 8 hours to complete the spec CPU benchmarks on an x86 server and more than 24 hours on an ARM device. Another problem is DBT runs on hardware platforms with various computation power, from low-end IoT devices to powerful high-performance servers. Using the same benchmarks for different platforms may lead to either long testing time or inaccurate testing results. To address these difficulties of applying performance regression testing for DBT systems, a straightforward thought is to shrink the input size of the DBT system. However, the input of DBT is executable binary, not regular data, so it is hard to manipulate the binary and reduce its size. Alternatively, we can input smaller data to the test programs, because standard test suites usually come with datasets in different sizes. However, the smaller datasets are only for functionality testing, which cannot produce accurate performance results, and typically only the largest ones are designed for performance testing. To summarize, simply shrinking the input size of DBT systems does not work. So it would be desired if we can come up with a more intelligent approach to improve the performance testing efficiency of DBT systems. To achieve a fast and adaptive performance regression testing for DBT systems, our idea is generating test programs by learning from standard benchmarks. This approach first learns the behaviors of standard benchmarks and then reconstructs test programs with the learned behaviors preserved. Afterwards, these test programs can be used for performance regression testing of DBT systems. By adjusting the workload, they can achieve a higher testing efficiency. Moreover, the testing effectiveness is very close to the original test benchmarks because the test programs can emulate the behaviors of the standard benchmarks. In addition, these test programs can be scaled up and down adaptively to fit different hardware platforms. Based on this approach, we design a testing framework called FADATest. Now, let's see how FADATest is designed. The first design issue is what program behaviors to learn. Briefly speaking, the behaviors that can help reconstruct more efficient test programs need to be kept. To address this issue, FADATest learns the instruction execution behaviors and thread activity behaviors from the standard benchmarks. The next design issue is how to generate a test program from the learned behaviors. FADATest solves this issue by reorganizing code blocks and recovering thread behaviors. Here is an overview of how it works. It contains 3 major steps. First, The hotness of executed hot blocks for each thread is recorded by profiling. Next, thread activity behaviors are also extracted, which include workload and liveness of each thread. Finally, with the above information, FADATest is able to generate more efficient test programs. Now, let's see some details of the 3 steps. The first step is code block hotness profiling. The purpose is to get the information of dynamically executed instructions of the original benchmark. This information can be used to recover the workload behaviors in program generation. FADATest adopts binary instrumentation for the code block hotness profiling. The hotness of a code block means the execution times of the block, while the hotter ones are more representative in the test. As a result, each block is labeled with the execution times in each thread. So the hottest blocks of each thread can be identified by ranking. And by selectively executing the hottest blocks and scaling down the execution times, there is a chance to reduce the testing time, but it won't produce accurate test results without recovering the thread behaviors. Next, let's move to the second step, how to recover the thread behaviors. With recovering thread behaviors, FADATest is able to generate test programs with similar thread activities as the original benchmark programs. Thread behaviors include thread grouping and thread activities. Let me first explain what is thread grouping. Usually, multi-threaded programs provide a parameter to tune the number of the threads. For example, like n thread here. What's interesting is we found in many benchmark programs, the actual number of threads is not equal to this parameter. Further analysis shows that these programs have thread groups, while threads in the same group do the same work. And the parameter n thread may affect the number of threads in each group in different ways. For example, in this figure, there are 3 groups, which are main, worker, and IO. Main group and IO group always have 1 thread of each, while the number of worker threads is determined by the input parameter n thread. FADATest recovers the thread grouping pattern by identifying threads with the similar workload. Given the thread grouping pattern recovered with a specified parameter n thread, the generated test program is able to create proper threads. Next behavior is the thread activities, which means the state of a thread, such as creation, termination, or hibernation. FADATest can get this information through the state benchmark program profiling. To summarize, with the information of block hotness and thread activities, FADATest is able to generate a test program with higher testing efficiency. Now, let's take a look at how a test program is generated. FADATest generates test programs in C language with assembly inline. Code blocks extracted from the original benchmark are embedded in the program as the workload. There are also loops outside to control the iteration. Workload is organized as thread group functions to match the original pattern. In the main function, there is the thread activity control, which starts or terminates a thread at a proper time. From the program, we can see that it is quite flexible to adjust the iteration and the thread numbers to adapt different hardware platforms. However, simply reassembling instructions will lead to crash. This may be caused by several reasons, for example, illegal memory access, illegal instructions, or exceptions triggered. To ensure the test programs can complete normally, we also do some instruction instrumentation for the inserted blocks. Please see our paper for more details. With these steps, FADATest can get effective test programs to improve the test efficiency for performance regulation testing of DBT systems. We have implemented FADATest to support two mainstream architectures on the market, includes x86-64 and ARC-64. To evaluate FADATest, we first generate test programs from standard test suites, spec CPU, and parsec. Here, we would like to point out that the programs generated by FADATest are not limited to any particular DBT system. For example, in our evaluation, the generated programs are used to test two DBT systems, which are QEMU and Valgrind. Now, let's see some results. First, let's see the effectiveness. Effectiveness means if the test programs generated by FADATest can discover the same performance issues as those found by the original benchmarks. Besides, to reflect the adaptability for multi-threaded benchmarks, we learn from 1, 2, and 4 threads configuration, while the generated test programs run with 8 threads configuration. And the baseline, the original benchmarks, also run with 8 thread configuration. The normalized testing time is shown in these figures. While 8 QEMU versions are tested, the curves indicate the performance changes among these versions. As we can see, FADATest produces very similar results to the original tests. In other words, the performance issues discovered by the original benchmarks can also be discovered by FADATest. Next, let's see the efficiency. We compare the absolute execution times of test programs generated by FADATest to the original benchmarks. The speedups are used to represent the testing efficiency. This figure shows the results of testing QEMU and Valgrind on different hardware platforms. Since FADATest scales down the workload hundreds times than the original test, we can see significant improvement in the figure. As a result, test programs generated by FADATest run up to 96 to 248 times faster than the original benchmark programs. Besides effectiveness and efficiency, we also studied the overhead of FADATest. Please refer to our paper for more details. To conclude, this paper proposes FADATest, which can provide fast and adaptive performance regression testing of DBT systems. FADATest first learns the workload and the thread behaviors from standard benchmarks, then automatically generates high-efficient test programs with the original accuracy preserved. It can also adapt various hardware platforms with different computation power. This is my presentation, and I'd be more than happy to take questions. Thank you.